Welcome! Today, we'll explore LeetCode problem number 1685, sum of absolute differences in a sorted array. This problem challenges us to compute the sum of absolute differences for each element in a sorted array efficiently. Let's dive in and break it down step by step. The problem asks us to calculate the sum of absolute differences between an element in a sorted array and all the other elements in that array. Specifically, we are given a zero-indexed array called nums, which is sorted in non-decreasing order. For each element in nums, we need to find the sum of the absolute differences between that element and every other element in the array. The result will be a new array of the same length as nums, where each position I contains the calculated sum for nums, I. To summarize, the task is to compute these sums efficiently for each element and return the resulting array. Let's consider the first example where the input array is nums equals 2, 3, 5. For the first element, nums 0 equals 2, the sum of absolute differences is calculated as the sum of the differences between 2 and every other element. 2 2 plus 2 3 plus 2 5 equals 0 plus 1 plus 3, which equals 4. For the second element, nums 1 equals 3, we calculate 3 2 plus 3 3 plus 3 5 equals 1 plus 0 plus 2, resulting in 3. Finally, for the last element, nums 2 equals 5, the calculation is 5 2 plus 5 3 plus 5 5 equals 3 plus 2 plus 0, which equals 5. Thus, the output array for this example is 4, 3, 5. Now, let's look at a slightly larger example with nums equals 1, 4, 6, 8, 10. For the first element, nums 0 equals 1, the total difference is 1 1 plus 1 4 plus 1 is 6 plus 1 8 plus 1 10 equals 0 plus 3 plus 5 plus 7 plus 9, which gives 24. For the second element, nums 1 equals 4, we calculate 4 1 plus 4 4 plus 4 6 plus 4 8 plus 4 10 equals 3 plus 0 plus 2 plus 4 plus 6, resulting in 15. Similarly, for nums 2 equals 6, the sum is 6 1 plus 6 4 plus 6 6 plus 6 8 plus 6 10 equals 5 plus 2 plus 0 plus 2 plus 4, which equals 13. For nums 3 equals 8, the sum is 8 1 plus 8 4 plus 8 6 plus 8 8 plus 8 10 equals 7 plus 4 plus 2 plus 0 plus 2, which gives 15. Lastly, for nums 4 equals 10, the sum is 10 1 plus 10 4 plus 10 6 plus 10 8 plus 10 10 equals 9 plus 6 plus 4 plus 2 plus 0, resulting in 21. The final output array is 24, 15, 13, 15, 21. Thus, the result for the second example is 24, 15, 13, 15, 21. The problem also comes with several constraints to consider. The array nums will always have at least 2 elements and at most 100,000 elements, and all values in nums will be between 1 and 10,000. Additionally, since nums is already sorted in non-decreasing order, we can take advantage of this property to optimize our solution. Some edge cases to consider include scenarios where nums contains only 2 elements, or all elements are identical, or where the input size is at its maximum limit. Furthermore, when the elements of nums are very far apart, we must ensure our solution handles the large differences efficiently without unnecessary computations. To solve the problem of calculating the sum of absolute differences for each element in a sorted array, we start by understanding the formula. For each element nums, I, the result is the sum of the absolute differences between nums, I, and every other element in the array. While a brute force approach is straightforward, it involves iterating through the array for every element, making it computationally expensive. Specifically, for each index I, we calculate the absolute difference between nums, I, and all other elements nums, j, then sum these differences. This involves initializing the result for each element, iterating through the array, and performing the summation. While simple to implement, the nested iterations make this approach inefficient for large inputs. The brute force approach has a time complexity of O(n squared), because we must iterate through the array for every element, resulting in nested loops. The space complexity, on the other hand, is O(1) if we exclude the result array, as no additional data structures are used. However, this approach becomes impractical as the array size increases, especially when n is as large as 100,000. To improve efficiency, we can exploit the fact that the array is sorted. By leveraging this property, we can use an optimized method involving prefix and suffix sums, which reduces the time complexity to O(n). This approach breaks the computation into two parts: the contribution of elements to the left of nums, I, and the contribution of elements to the right. For elements on the left, the contribution is proportional to their distance from nums, I, while for elements on the right, the contribution works similarly but in reverse. To efficiently compute the sum of absolute differences, we use prefix and suffix sums. First, we calculate a prefix sum array, where each entry represents the cumulative sum of elements up to the previous index. Similarly, we compute a suffix sum array, where each entry represents the cumulative sum of elements from the next index onward. Using these pre-computed arrays, we can determine the result for each element in constant time. For an index I, the contribution of elements to the left is calculated as I** nums, I, prefix, I, and the contribution of elements to the right is suffix, I, and I1** nums, I. Combining these two parts gives the result 4 nums, I. This method reduces redundant calculations, achieving a time complexity of O(n) for both the prefix and suffix sums, as well as for calculating the results. The space complexity is O(n) due to the additional arrays, but this trade-off is acceptable given the significant improvement in speed. Ultimately, we chose the optimized approach using prefix and suffix sums because it achieves linear time complexity, making it suitable for handling large inputs up to the problem's constraints of 100,000 elements. The key insight is leveraging the sorted nature of the array to reduce redundant computations, ensuring efficiency and scalability. While the brute force method is easier to implement, its O(n)² complexity is prohibitively slow for large arrays. In contrast, the optimized approach, though slightly more complex, is significantly faster and scales well due to its O(n) complexity. By balancing time efficiency and additional space usage, this approach is the most practical and effective solution to the problem. To solve the problem, sum of absolute differences in a sorted array, we need to efficiently compute the sum of absolute differences for each element in a sorted array. Instead of using a brute force approach, which would have a time complexity of O(n)², we can leverage the sorted property of the array to optimize the process. The problem involves calculating the sum of absolute differences between each element and all other elements in the array. For example, given the array 2, 3, 5, the output should be 4, 3, 5. This is because, for the first element 2, the sum of differences is 2-2 plus 2-3 plus 2-5, which equals 4. Similarly, for the second and third elements, the sums are 3 and 5, respectively. With this understanding, we can now explore how to compute these sums efficiently without resorting to nested loops. The key to optimization lies in breaking the problem into two parts: the left contribution and the right contribution for each element in the array. The left contribution represents the sum of absolute differences for all elements to the left of the current element, while the right contribution represents the sum for all elements to the right. Because the array is sorted, we can use this property to compute these contributions efficiently. To facilitate these calculations, we introduce the concept of a prefix sum array. This array allows us to pre-compute cumulative sums of the elements in the array, enabling quick access to the sum of any subarray. For instance, the prefix sum at index I provides the sum of the first I elements. This eliminates the need to recompute sums repeatedly, saving significant computation time. Using the prefix sum array, we can calculate the left and right contributions for each index. For the left contribution, we multiply the current index by the value at that index and subtract the prefix sum of all preceding elements. If there are no preceding elements, the left contribution is simply 0. For the right contribution, we calculate the difference between the total sum of the array and the prefix sum up to the current index. We then subtract the product of the number of elements to the right of the current index and the value at the current index. Combining these two contributions gives the result for the current index. This approach ensures that we compute the result for each index in linear time, avoiding the inefficiencies of a nested loop approach. By decomposing the problem into left and right contributions, we reduce the time complexity from O(n)² to O(n). This improvement is achieved by leveraging the prefix sum array, which allows us to compute cumulative sums in constant time. This method is both scalable and efficient, handling edge cases naturally. For example, in a single element array, the result is simply 0, as there are no other elements to compare against. Similarly, in a uniform array where all elements are the same, all absolute differences are 0, resulting in an output filled with zeros. The use of the prefix array also ensures that the algorithm performs well for large inputs, maintaining linear time complexity while requiring only linear space for storage. The implementation of this algorithm begins with constructing the prefix sum array. Starting with the first element, we iteratively compute the cumulative sum for each index. Then, we initialize the result array, which will store the final output. For each index, we calculate the left and right contributions using the formulas derived earlier. The left contribution depends on the prefix sum of preceding elements, while the right contribution uses the total prefix sum and the remaining elements to the right. Finally, the two contributions are combined and stored in the result array. Once the iteration is complete, the result array is returned as the solution. This implementation is efficient, clean, and aligns perfectly with the optimized algorithm we've developed. To solve LeetCode problem number 1685 efficiently, we utilize prefix sums to calculate the sum of absolute differences for each element in the sorted array. Here is a detailed explanation of the code. 1. Initialization. We start by determining the size of the input array nums and initializing an array result of the same size to store the final outputs. A prefix _sum array is created to store cumulative sums of the elements in nums, which helps in efficient range sum calculations. 2. Building the prefix sum. The prefix _sum array is filled such that prefix _sum, I, contains the sum of the first I elements in nums. This is done iteratively, where each element is the sum of the previous element in prefix _sum and the corresponding element in nums. 3. Calculating the result for each index. For each element nums, I, we calculate its contribution to the sum of absolute differences using two parts. Left contribution, the sum of differences between nums, I, and all elements to its left. This is computed as nums, I, asterisk I prefix _sum, I. Right contribution, the sum of differences between nums, I, and all elements to its right. This is computed as prefix _sum n, prefix _sum, I plus 1, nums, I, asterisk, n I1. The total contribution for nums, I, is the sum of the left and right contributions, which is stored in result, I. 4. Returning the result. Finally, the result array is returned as the output, containing the sum of absolute differences for each element in the input array. This approach is efficient, with a time complexity of O(n), since we process the array linearly multiple times, once for prefix sum calculation and once for computing results. This is a significant improvement over the naive O(n)² approach where we would calculate absolute differences for each pair of elements directly. This is the Java implementation of LeetCode problem number 1685, sum of absolute differences in a sorted array. The code mirrors the Python logic, converting it into Java style with explicit type declarations and Java-specific constructs. It calculates prefix sums to optimize the computation of absolute differences and constructs the result array efficiently. The class is complete with all necessary methods and imports. In this problem, we are given a sorted array nums, and our goal is to compute a new array result. Each element result, I, in this array represents the sum of the absolute differences between nums, I, and every other element in nums. To solve this efficiently, we start by calculating the prefix sum of the input array. The prefix sum allows us to quickly compute the sum of any subarray. For example, if nums is 2, 3, 5, we initialize prefix _sum as an array of zeros with a length of n plus 1. This ensures we have an extra slot to accommodate sums up to any index. Starting with I equals 1, we calculate each prefix _sum, I, as the sum of prefix _sum, I1, and nums, I1. So, for I equals 1, the prefix sum becomes 0, 2, 0, 0. For I equals 2, we add nums, 1, to the previous sum, resulting in 0, 2, 5, 0. Finally, for I equals 3, we add nums, 2, giving us 0, 2, 5, 10. This prefix sum array will help us efficiently calculate sums for the next step. Now that we have the prefix sum, we proceed to compute the result array. We initialize result as 0, 0, 0, corresponding to the length of nums. For each index I, we break down the calculations into two parts, the sum of elements to the left of nums, I, and the sum of elements to the right. For I equals 0, nums, 0, is 2. The left sum is 0 because there are no elements to the left. The right sum is calculated as the sum of all elements to the right, adjusted for their distance from nums, 0. Using the prefix sum, this gives us 4. Adding the left and right sums, we get result, 0, equals 4. For I equals 1, nums, 1, is 3. The left sum is the total of elements to the left, adjusted by their distance, which is 1. The right sum is the total of elements to the right, adjusted similarly, which is 2. Adding these, we get result, 1 equals 3. Finally, for I equals 2, nums, 2, is 5. The left sum is 5, and since there are no elements to the right sum is 0. This gives result, 2 equals 5. The final result array is 4, 3, 5. Let's look at another example where nums is 1, 4, 6, 8, 10. The first step is to compute the prefix sum. Starting with an array of zeros of length n plus 1, we calculate each entry by adding the corresponding nums value to the previous prefix sum. This gives us 0, 1, 5, 11, 19, 29. Next, we calculate the result array using the same approach as before. For I equals 0, nums, 0, is 1. The left sum is 0, and the right sum is the total of elements to the right, adjusted for their distances, which gives 24. So, result, 0, equals 24. For I equals 1, nums, 1, is 4. The left sum is 3, and the right sum is 12, giving result, 1, equals 15. For I equals 2, nums, 2, is 6. The left sum is 7, and the right sum is 6, so result, 2, equals 13. For I equals 3, nums, 3, is 8. The left sum is 13, and the right sum is 2, giving result, 3, equals 15. Finally, for I equals 4, nums, 4, is 10. The left sum is 21, and there is no right sum, so result, 4, equals 21. This results in the array, 24, 15, 13, 15, 21. For a final example, let's consider a smaller array nums equals 1, 2. The prefix sum here is straightforward, 0, 1, 3. Using this, we calculate the result array. For I equals 0, nums, 0, is 1. The left sum is 0 since there are no elements to the left, and the right sum is 1, which gives result, 0, equals 1. For I equals 1, nums, 1, is 2. The left sum is 1, and with no elements to the right sum is 0, resulting in result, 1, equals 1. The final result is 1, 1. This demonstrates how the approach works for arrays of any size, leveraging the prefix sum to achieve efficient computation. To analyze the time complexity of the solution, we start by breaking it into two main operations. First, there's the prefix sum calculation. Here, we create an array called prefix_sum with a size of n plus 1 and compute the cumulative sums for the elements in the input array nums. This involves a single loop that iterates from 1 to n, and since each iteration performs a straightforward addition operation, the step runs in n time. Next, we focus on the result calculation. For each element in nums, we compute contributions from the left and right sides. The left contribution requires one multiplication and one subtraction, both of which take constant time, or O1. Similarly, the right contribution involves two subtractions and one multiplication, so this step is also O1. Since we process each of the n elements in nums exactly once, the result calculation also runs in n time. Combining these two steps, the overall time complexity of the solution is n. With both the prefix sum calculation and the result calculation each taking n, the total time complexity becomes n plus n, which simplifies to n. This is an efficient approach because each element in the array is processed a constant number of times. Now, let's analyze the space complexity. First, we have the input array nums, but since it's provided as input, it doesn't contribute to additional space usage. Then, there's the result array, which stores the output and has a size of n, contributing n space. We also use the prefix_sum array, which has a size of n plus 1, also contributing n space. Beyond these, we only use a few variables like n, I, left underscore sum, and right underscore sum, which require constant space or 1. Adding these together, the total space complexity is n plus 1 plus 1, which simplifies to n. Let's compare this optimized approach to a brute force solution. In the naive approach, for each element nums, I, the sum of absolute differences would be computed by iterating through the entire array. This would require n iterations for each of the n elements, resulting in a time complexity of n squared. While the space complexity in the brute force approach could be 1 if no additional arrays are used, the high time complexity makes it impractical for large input sizes. In contrast, the optimized approach leverages prefix sums to avoid redundant calculations. By pre-computing cumulative sums, we can calculate contributions in constant time for each element, reducing the time complexity to n. The space complexity remains n, due to the use of the prefix underscore sum and result arrays. This is a significant improvement in efficiency, especially for larger arrays. The mathematical justification for the optimized approach holds since both the prefix sum calculation and the result calculation involve single traversals of the array, each taking n. Finally, let's look at the best, average, and worst case analysis. Since the array is always sorted, the number of operations remains consistent regardless of the input. This means the solution performs in n time an n space in all cases, whether it's the best, average, or worst case. The optimized approach takes advantage of the sorted nature of the array and the use of prefix sums to achieve linear time complexity. Compared to the quadratic time complexity of the brute force method, this is a dramatic improvement, making the optimized approach highly suitable for large input sizes, such as when n is up to 10 to the power of 5. By reducing redundant computations and utilizing efficient data structures, the solution is both fast and scalable, ensuring it performs well even under demanding scenarios. One of the most common mistakes when solving this problem is using a brute force approach, especially for large arrays. Calculating the absolute difference for every pair results in n squared complexity, and this becomes impractical for large inputs like n equals 10,000, often leading to time limit exceeded errors. Instead, you should take advantage of the sorted nature of the array and use prefix sums to reduce the time complexity to n. Another frequent issue is miscalculating the contributions of elements before and after the current element. For instance, many overlook that the prefix contribution is added, while the suffix contribution is subtracted. The correct formula involves two parts: the prefix, which is calculated as I times nums, I, minus the sum of all elements before it, and the suffix, derived from the total sum minus the suffix sum so far, adjusted for the number of remaining elements. Finally, initializing prefix and suffix sums incorrectly can also lead to problems. Always ensure that prefix sums start at 0 for the first element and are updated cumulatively to avoid errors in your calculations. Another pitfall is misunderstanding the significance of the sorted property of the input. If you ignore that the array is already sorted, you might end up performing redundant checks or adding unnecessary complexity to your solution. Instead, leverage this sorted property to streamline calculations, such as focusing on differences between consecutive elements rather than arbitrary pairs. Edge case handling is another critical area where mistakes occur. For example, single-element arrays or arrays where all values are the same can cause runtime errors if not properly addressed. Testing with cases like an array containing just one element or arrays with uniform values, such as 5, 5, 5, 5, will help you ensure your solution handles these scenarios robustly. From an interview perspective, this problem is an excellent opportunity to showcase your ability to optimize for n solutions by using cumulative sums. Prefix and suffix sums are recurring patterns in many computational problems, so mastering them not only helps here but also saves time in similar scenarios. When discussing with an interviewer, always clarify constraints like the input size and explicitly discuss how you plan to optimize for large arrays. Walking through a small test case can effectively demonstrate your understanding of the prefix-suffix approach. This problem is closely related to several others that can help you further practice and refine your understanding of prefix and suffix sums. For instance, LeetCode 303, Range Sum Query Immutable, focuses on using prefix sums to optimize range queries efficiently. Another example is LeetCode 238, product of array except self, which involves a similar concept of prefix and suffix arrays, though applied to products rather than sums. LeetCode 724, find pivot index, also emphasizes balancing prefix and suffix sums to identify the pivot point in an array. Lastly, LeetCode 1774, closest dessert cost, presents a more advanced scenario requiring careful cumulative calculations. By exploring these related problems, you can solidify your grasp of cumulative computation techniques and expand your problem-solving toolkit. There are several approaches to solving this problem, each with its own trade-offs. The brute force method, which involves calculating absolute differences for every pair in the array, is simple to implement but highly inefficient with n² time complexity. While it works for small arrays, it quickly becomes impractical for larger inputs. A more efficient approach leverages prefix and suffix sums to achieve an O(n) solution. By calculating prefix and suffix sums in a single pass, you can optimize the computation significantly. The trade-off here is that the implementation is slightly more complex, but the scalability makes it worthwhile for larger arrays. Another technique, the sliding window approach, can be useful in specific scenarios where dynamic tracking of sums is required. However, this method is limited to cases with adjustable windows and is not as broadly applicable as the prefix-suffix strategy. Understanding these alternatives allows you to select the most appropriate method based on the problem's constraints and input size. Great job! To recap, we solved the problem using an efficient algorithm that leverages prefix sums and the sorted nature of the array. Remember to practice this technique for similar problems. Thanks for joining, and don't forget to like and subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!